Trigonometry, Chapter 2, Acute Angles and Right Triangles, Section 3, Approximations of Trig Function Values, Video 4, Application, Design of Highway Curves. This series is based on content from Pearson's 12th Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned how to calculate the grade resistance of a vehicle traveling along an inclined road. If the road has a grade of theta, measured in degrees, and the weight of the vehicle is W pounds, then the grade resistance in pounds is F equals W sine theta. In this video, we calculate the safe radius of a curve for a given inclination of a highway. In other words, when you're driving down the highway at a high speed and the highway has a curve, the road is going to be tilted some to mitigate the effects of centripetal force. When highway curves are designed, the outside of the curve is often slightly elevated or inclined above the inside of the curve. This inclination is called the superelevation. For safety reasons, it is important that both the curve's radius and the superelevation be correct for a given speed limit. Specifically, if an automobile is traveling at velocity v in feet per second, the safe radius of curvature r in feet for a curve with superelevation theta is modeled by the formula r equals v squared all over g times the quantity f plus tangent of theta, where f and g are constants. And just for clarification, radius of curvature is the radius of the circle of which the curve would be an arc. For example, a roadway is being designed for cars traveling 60 miles per hour. If theta equals 4 degrees, the superelevation, g equals 32.2, and f equals 0.14, calculate r to the nearest foot. So we use our formula, but first, we must convert the speed to feet per second as required for the formula. If you go back and see, it says here that the velocity is in feet per second. So we need to convert 60 miles per hour to feet per second. And we can do this using dimensional analysis or unit analysis by multiplying by ratios of equal units that will cancel the given units and bring in the desired units. For example, I want to eliminate hours and replace it with seconds, so I'm going to multiply by 1 hour over 3,600 seconds. That means eventually, and I guess I could do it right now, we could cancel the hours. Then we'd have miles per seconds, but we want feet per second, so we need a ratio that changes miles to feet. That ratio is 5,280 feet to 1 mile. And again, the hours would cancel, the miles would cancel, and the remaining units would be feet per seconds. So if we do 60 divided by 3,600 times 5,280, we would get exactly 88 feet per second. For those going towards the physics or engineering direction, memorizing 60 miles per hour equals 88 feet per second is incredibly handy. Saves you all this trouble. All right, so now that we have the velocity is 88 feet per second, we can use the formula to calculate the radius of curvature. Recall that theta equals 4 degrees, g equals 32.2, and f equals 0.14. So this is literally plug in the values and simplify the expression. Here's the formula with the values inserted. And if you put this into your calculator correctly, and it's in degree mode, you should get a radius of curvature of about 1,146 feet. And that's a pretty big circle. That's about a fifth of a mile, a little less than a fifth of a mile, a little more than a fifth of a mile. But if you're turning 60 miles an hour, you need either steep incline or large radius to prevent centripetal force from flipping your car. So big radius it is. You don't want the big incline because either your car might tip over if you're going too slow, or if you're going too fast, the centripetal force could actually push you into the seat and make it rather uncomfortable. Now you try. Pause the video and try the following. Sometimes we can't control the radius of curvature and have a specific value of superelevation for safety purposes and need to determine a safe speed limit. Suppose we're building a highway whose radius of curvature is 1,150 feet with a superelevation of 2.1 degrees. Using the same F and G as before, What should the speed limit be in hours? What should the speed limit be in miles per hour? Pause the video and give it a try. All right, here's your fair warning. Solutions in 3, 2, 1, but I'm going to go over this solution. So it's a little bit longer than the video normally would be. If we're going to solve for v, we need to substitute all the values like we did before. But this time we know the radius and we have the constants and we know the inclination, super elevation, excuse me, and we're solving for v squared. So how can you solve something like this? The inclination on some people, no pun intended, is to start figuring out what this denominator equals and then going from there. My advice is don't put anything into your calculator until the last moment, because if you were to evaluate the denominator, you are going to round off your answer because it would be an irrational number whose decimal goes forever. Therefore, you're introducing some inaccuracy to your answer, and further calculations could compound that inaccuracy. Instead, I would put the calculator down and do some algebra moves, particularly to solve for v squared, you could multiply both sides by the denominator. If you multiply both sides by the denominator, and I'm not going to rewrite the entire denominator, but if I wrote the denominator here and here, then it would cancel out and it would leave me v equals, well, and then take the square root of both sides. Then it would leave me v equals the square root of this expression, which ends up being about 80.88 feet per second. And if you convert that back to miles per hour, you get 55 miles per hour. So this is how they kind of determine the speed limits, especially on curvy roads, based on the radius of curvature and the relationship to the velocity, the safe velocity, if you will.